Okay, so let us start. So welcome to session 10, that is week 10 of this course, Parameterized Algorithms. So this is the 10th week. So we are towards the end of this course. And the last session, that is the 12th session, is scheduled on 14th October, which is a Monday. So after that, there is going to be one more session, which is an extra session that is going to happen tentatively on 21st October. And in that session, we will discuss two concrete problems. Uh, in one of these problems, we are going to look at some fixed parameter tractable algorithm for that problem. And the other problem will be something that uh, we will decide. In fact, one of the problems has been suggested by Mr. Goel. And beyond that, we will conclude the course on 21st October. So without further ado, let's get started. So this is question one of today's session. So you are given a graph, and the question is about graph coloring. So in the graph coloring question, uh, you are supposed to find the minimum number of colors to be assigned to the vertices such that no two adjacent vertices receive the same color. And this is an NP-hard problem to minimize the number of colors required. So there is some algorithm which runs in 3 to the power n running time, where n is the number of vertices. And there is a description of that algorithm in module 10, lecture 39. So in that DP, they do certain things. So the question is based on that DP. But even if you have not watched the video lecture 39, you should still be able to answer this question. So I will let you read the question for some time, then I will proceed.
So we compute and store AX and then the chromatic number of GX for the graph this thing. And then all the statements are about this AX. But then I could not understand, the difference in between this AX and GX. Like GX is because we compute the chromatic number for the graph as a whole, the minimum number of the colors required to paint the graph without violating the constraints.
Correct.
So what is X here is, P of X here.
So X is a subset of the vertices,
Okay,
and Gx is the graph induced on X, the subgraph induced on X. So
Mhm.
in AX, we are supposed to store the chromatic number of the subgraph induced on X, that is Gx. So
Okay, I understood. Fine. So if you do not have any vertex, like say if X is equal to 5, so then we don't require. So doesn't matter that whether so minimum number of the colors required. Since the GX is the chromatic number, so this minimum term is there. So therefore, the A of 5 would be equals to 0. We do not require anything.
that is
Uh,
true.
yeah, and if we only only take one vertex, say U, then I would be requiring one color without violating the constraint. So AU 0 would be false, but then AU 1 would be equals to true. Uh, yeah, I think AU is equal to 1 would be true. And then AU comma X. So if I take U and then X, then definitely since U and X are adjacent, so I would be requiring, say, minimum two colors to paint the things. So therefore, AU comma X is equal to 2. I mean, one color won't be sufficient, reason being, yeah, because of the obvious reasons. And then a W comma V. So if I take W and V, since W and V are not adjacent, so I think that, and if I only take this W and V, So, I mean, both can be painted with the same color. There would be two separate vertices in the pool. So, yes, this is true. And if we take U, V, and then W, so if I take this thing, then I would be requiring minimum two colors I would be requiring, and because W and V are not adjacent, so two would be sufficient. So yes, this is true, and the last one is false. And then they are asking that the chromatic number of what is the chromatic number of the graph as a whole as such. So if I paint the U with one color, so then I cannot paint W with the same color and X with the same color. So I would be requiring minimum three colors because yeah, because U, W, and V. So these, I mean, because the degree of the vertex U is 3, so therefore I would be requiring at least three colors in any case. But yes, so but if I use three colors, so I can not paint X with the same color then, because the color of because X is also having three, so the chromatic number of the graph is 4.
So the chromatic number of the graph is 4 based on your observation that U has degree 3.
Not only this one, because I mean, because the degree is 3, so I thought of giving the answer as 3. But then I observed that this x is also adjacent to u. And so therefore, I would be needing a separate, and x moreover is adjacent to the v and w as well. So I would be requiring one additional color here. So yeah. And then because I vaguely remember one algorithm, and that used to be, I forgot it, not flurry algorithm, but then so that using that algorithm we used to find the upper bound over the number of the colors required, and I just forgot the name of the algorithm. So that does not compute the chromatic number, but then gives
Hmm.
the upper bound of the number of the colors.
Okay. So what is that upper bound?
So upper bound here comes out to be, I mean, 4. So I mean, with the 4 number of the colors, definitely we can paint this graph because so in that algorithm, what happens that we used to maintain a list in say in the decreasing order of the degrees of the vertices, and then
Okay.
we paint the first vertex with a color, and then we go, and then we scan the entire list and find a vertex which is not adjacent to the one which has already been painted, and we keep on repeating this process and we get the upper bound of the number of the colors required.
Okay. So you do something greedy and
Yes.
okay. So uh, so let me first write down the DP so that we can be more precise and formal. So the DP is the following. So AX. So AX is the chromatic number of GX. That is the subgraph induced on the vertex at X. So AX, as per the DP recurrence, is the minimum over all Y, which is a subset of X, uh, proper subset, minimum of minimum over all Y, 1 plus A of X minus Y. Okay, so what does this mean? So this means, uh, okay, so what else? And Y is what? Y is an independent set. So consider a non-empty subset Y of X such that Y is an independent set. So additionally, Y is an independent set. Let's say that to compute the chromatic number of this subgraph induced on X, first find a subset of X which is an independent set. So because Y is an independent set, all the vertices of Y can be given the same color. Now, this one color you have used to color the vertices of Y, that is one already used. Additionally, the remaining vertices, that is X minus Y, have to be colored. But since we are doing DP, so smaller instances can be looked up from the table. So that means X minus Y is corresponding value, that is A of X minus Y, is supposed to be computed earlier. So you already know this. Now, given that you know this and you also have identified Y to be an independent set, you will require 1 plus so many colors to properly color the subgraph induced on X. Now, since you are taking minimum over all such independent sets, you are going to find the minimum of them, and that is going to be your chromatic number for Gx. So this is the idea behind the recurrence. So is the recurrence all right?
Yes, yes, yes. So can we say anything about the number of the independent sets of a subgraph? Do we have, I mean, do we know
Yes,
something
yes, yes.
concrete?
So for
And
example, if X is 4 vertices, then there are 2 to the power mod X, that is 2 to the power 4, that is 16 possible subsets of X. And for all such subsets, you have to check whether you can uh, consider it to be an independent set. So for X, you may have to consider 2 to the mod X possible subsets of X as possible candidate independent sets. So that is why the running time will sort of become exponential.
yes, so, but I have a little apprehension here that because we usually use dynamic programming when we find that we have a large number of the possibilities, and so we want to give a try to solve that problem in the polynomial time. So then we go for the DP thing, and however the DP itself is taking an exponential time. So what's the fun and what's the use of, I mean, solving a problem in the exponential time using DP?
So this is an NP-hard problem. So
Yes.
we are not going to get anything better than exponential. So if we are insisting that we must find the exact chromatic number, then exponential time will be required. So if you are insisting that no, chromatic number is chi, and I am happy if you give me some additive factor. Maybe I'm happy if you give me some chromatic number, some coloring that requires 100 more colors. So you are okay with some approximation, or if you say that I'm okay with 3 chi colors, then you can hope for something sub exponential running time. But since this algorithm, this dynamic programming algorithm is going to give you the exact chromatic number, so better than exponential time algorithm would mean P equals NP. So why we are doing the DP is just we are compromising on the running time. And there's not much we can do when we are insisting on finding the exact chromatic number.
Okay. Okay. Yes. Yes.
So, but this 3 to the power n can be reduced to some 2.4 to the power n running time, and that is there in the lecture. So, there is something called the inclusion exclusion principle, and with that principle, uh, uh, the running time was reduced substantially. So, 2.4 to the power n or slightly less than that is possible, but then again, it is exponential time. But if you are happy with the approximations. So there are some algorithms, for example, for 3 colorable graphs. Uh, so if you know that a graph is already known to be 3 colorable, that 3 colors will suffice, then how many colors? Then in some polynomial time, people have given colorings that requires, let us say. So I don't exactly recall, but with substantially more number of using substantially more number of colors than 3, people can find in polynomial time coloring. So people can compromise on the uh, 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 chromatic number. That is, people can be happy with approximations at the gain of running time.
Yes. And in the computational complexity course, I mean, we studied one interactive proof system to, I mean, to get, I mean, to address this three colorable problem in a reasonable time and with lesser, I mean, margin of the error. I mean, so if we, I mean, continue, I
Yes,
mean, yes, such a proof system is there. I mean,
yes. Sometimes when you are happy with randomized algorithms, so with repetition, then the quality of the solution can increase with more iterations.
Yes, yes, yes.
So in this case, this is an exact algorithm. So we are finding the exact chromatic number, and this is going to give you the exact chromatic number, this DP recurrence. And this recurrence will apply on some subset X of V. So what is V? V is all the four vertices. So in this graph, there are four vertices. So if you take X to be three vertices, U, V, and W, so that is this, we have agreed that UVW's chromatic number, that is the subgraph UVW, this subgraph's chromatic number is 2, that we have agreed. So now that two colors are sufficient to color these three vertices, additionally to color X, take any other color. So let us say, let me give some colors. So let us say this is red, this is green, this is looking like green. Let's make it more bright green. So we have agreed that two colors are sufficient to color these three vertices. Now X can get anything other than red and green, so let's make it blue.
Oh yes, so I made this mistake.
Yes, yes, yes. So how we shall, so if we are blindly, or rather uh, religiously applying the DP, then we can see that, okay, to compute A of the entire vertex set is nothing. So see, one of the candidates would be that uh, X, this vertex X is an independent set. So now if you give it one color, so you are spending one color on X plus the chromatic number of the remaining vertices. So V minus this vertex, which is nothing but, what is it? U, V, and W. So you have already computed U, V, and W, and you have agreed that this is 2. So it is going to be one more than 2, that is 3. So one can do that TP business also, but naively one can also just look at the instance because it is small. One can find out the answer. So all these answers can be given just looking by looking at the small graph. So chromatic number, of course, 4 colors are also possible, but chromatic number is the minimum number of colors required. So that's why chromatic number is 3. All right. So fine. So this was about coloring. Okay, so this is question number 2. There are two graphs given to you. The question is, what is the chromatic number of each graph? Let me check. What is the question? Yeah. So the question is, which of the graphs admits 3 coloring? Or rather, we'll just find what is the chromatic. Let's say this is, so by chi, we mean the chromatic number. So let's say this is graph 1. So what is the chromatic number of 1? And what is the chromatic number of 2? That's all we are asking.
So for the chromatic number of the first graph, so because the labels are not assigned to the vertices, so uh,
Okay.
yeah, so if you can write the labels here, 1, 2, 3, 4. So I paint vertex number 1 with a color, say a color A, and then I paint the vertex number 6 with the color B and vertex number 2 with the color say C. Three colors have been used. So now I can reuse the color A for the vertex 7, and I can reuse the color say C for the vertex 3, and I can no see B, the color B, the remaining color B for the vertex 3, and the color C for the vertex 8, and then I can reuse the color A for the vertex 4, and the color B for the vertex 9, and then I can use the color C for the vertex 5, and the color A for the vertex 10. So maximum 3 colors are required to paint this graph.
Okay. This is a valid coloring. So you have been able to ensure that every adjacent vertex have received different colors. So this is fine. This is actually true.
So I
So,
focused on the triangle part.
mhm. So come again?
So I focused on the triangle part, that
Yes,
over
yes,
it
yes.
the color of the vertices should be.
Okay. So one can also try to reuse this recurrence. Of
Yes.
course, we can do it by, by manually looking at it the way you have done it. But one can also try to use this recurrence. So if somebody is following rules religiously, then one can see that, okay, can I find an independent set in this graph? And then on the removal of the independent set, so whatever is remaining, is it a bipartite graph? So first is to identify some set of vertices, which is an independent set. And then let me identify some vertices. So I will use the color red. So I am going to identify this vertex 2, this vertex 8, this vertex 5. So these three vertices form an independent set. And now on removing these three vertices, what we are left with is this graph. So this is the path, and the path is two colorable. So for the path, we can use two colors, and additionally one more color can be used for the independent set. So that is another way of concluding that 2 plus 1, 3 colors will be sufficient.
So I have a query here that in this recurrence relation, instead of removing, say, an independent set, I mean, we should focus on removing the largest independent set probably, and that may ease the solution, like we did in this case. So here, what is happening in the recurrence relation, that we are possibly we are considering all independent sets. So is this so,
Yes.
or otherwise? Yeah. So what if we remove the largest independent set from the pool, and we start with the removal of the largest independent set first? And will it affect the quality of the solution? I think, like in this case, yeah, we could immediately tell that the chromatic number would be equals to 3 because we removed the largest independent set that comprises of the three vertices.
So you are saying that this running time 3 to the power n can be reduced by making this uh, greedy choice. That is, instead of going over all the possible y's, just go and find the largest independence. So finding the largest independence that itself is NP hard. That is the other problem.
But then getting the number of the independent sets is not an easy problem, I think. Must be, I mean, comparable, I mean, would be equally hard, I guess. Getting the total number of the independent sets, because
Yes, yes.
then
So
we,
we are enumerating all the possibilities. So there
yes,
are exponential number of independent sets candidates.
yes.
Whereas finding the largest independent set itself is an NP hard problem. So your algorithm would first have to find out that how to find a large independent set.
But then, so if I can enumerate the number of the possible subsets at 2 raised to the power n, I can go through every vertex exactly once. So at the most, I would be solving this largest independent set problem in an effort of the order of 2 raised to the power n into 2 raised to the power n c. And that value comes out to be 2 raised to the power 2n, and which is again comparable to the 2 raised to the power n. Still exponential only.
So what is this expression?
So 2 raised to the power n plus n, or what? 2 raised to the power 2 raised to the power n square, I think.
Okay, so what is what is this quantity for?
So I think that this is also exponential only.
So that is fine. But what are you counting?
So I'm counting the possible number of the subsets, number one. So I have to
Okay,
reach n number of the possibilities, and then I'll go inside a loop, and which varies from say 1 to 2 raised to the power n, and while evaluating that whether the I
okay.
mean, yeah.
Whether it is an independent set or not, that you will check in each iteration.
So, so my point is that both the problems are equally hard.
Mhm.
Getting all the independent set for a graph and getting the largest independent set for a graph. Because once I have all the independent sets of a graph, then at the most, in the worst scenario, I'll
Mhm.
have to use the for loop varies from 1 to 2. See, assume that I have to raise to the power n number of the independent sets,
Mhm.
right? This could be the worst situation. Then at the most, I would be using additional for loop, which varies from 1 to 2 raised to the power n, to determine that which independent set out of these many possibilities is the largest one.
Correct. So
So
whether the largest independent set is going to help you or not, that also needs to be argued. So in this case, they are naive and they are not making any claims about which independent set is the most profitable. But uh, your algorithm would sort of believe that removing the largest independent set makes more sense than removing a smaller independent set. But that needs to be argued as well. So first observation is your running time is going to be roughly equal. Roughly, it is going to be 3 to the power n in the worst case. Uh, on the other hand, this rationale behind finding the largest independent set and then removing it to obtain the remaining graph, whether it yields some benefit or not, that is also not clear right now. So
so
maybe,
I
yeah, go ahead.
so yeah. At this point, my argument is that do we have some predefined structures? Like say, just now you mentioned that I mean for a straight line, the straight line is two colorable. I mean if I have a chain kind of the thing of the vertices, that
Yes,
is.
yes, yes,
So, I mean, don't I have predefined structures wherein I know this thing in advance that
yes, yes.
okay, such a structure is, I mean, its chromatic number would be like this. In the graph theory, there might be quite possible that there might be some well-defined structure. Now the argument is that after the removal of the largest independent set, I mean, what is the probability of having, I mean, transforming that graph into the well-known structures? So that I mean, if
So there is a straightforward rule. The rule is that a bipartite graph is two colorable. So if you can find a bipartite graph after removal of your independent set, then you know that two more colors will be sufficient.
yes, yes. Uh,
On the other hand, the three colorability question is NP hard. So the question that is a graph. So given a graph is three colors sufficient to answer that question is NP hard. So so we do not know that what are the kind of graphs for which three colors are sufficient. That we do not know.
oh, I see. But then, so this two colorable thing is a magical one. So if after the removal of the largest thing, I mean, so but then there would be very very limited cases wherein after the removal of the largest independent set, we come up with a thing, and which is two colorable because. We have polynomial time algorithms only for the things wherein we find two. Like say two set is polynomial and two colorable. I mean,
Yes.
Yes, yes.
So there is not much liberty you have. You can only try to see if you can obtain a bipartite graph by removing certain independent set. If it turns out to be a bipartite graph, you can say, okay, 2 plus 1 colors is sufficient. Otherwise, you have to sort of rely on this DP, and you have to keep on building this DP bottom up so that you know finally what is the total number of colors required.
Yes, yes, yes.
But as I mentioned that this running time 3 to the n can be reduced to 2 to the 2.4 to the n with some tricks.
But I believe that even if it is 2.4, it is not of much use unless I brought it down, say, to the level something like 1 point something. Then probably it will leave much impact. Uh,
Oh, so that is not even possible
right?
because because so this step that so as far as this algorithm is concerned, this step requires you to check whether you have an independent set, whether y is an independent set, and the possible number of candidate is itself 2 to the mod x. So in the
Oh,
worst case, it is 2 to the n.
yes, yes, yes.
So there is a lower bound of 2 to the n on the running time already. And in general, also, I think the lower bound of 2 to the n running time to find the exact chromatic number will be applicable, irrespective of this algorithm. So whatever may be the algorithm. So I think that is also discussed in the lectures that a lower bound of 2 to the power n will be applicable.
Okay,
Of course, it is not going to be any useful. So 2 to the n, even 2 to the n, practically speaking, it is not useful. But it turns out that with the tricks that they have, uh, so if you're happy with approximations, so for 3 colorable graphs, there are some results that, okay, the user is ready to compromise on the chromatic number, that is how many colors are required. So in reasonably good amount of time, one can, let us say, give you 100 coloring, whereas a 3 coloring is possible.
okay, okay. Mm.
So maybe this suggestion that you have made, that try to remove the largest independent set and on the remaining graph uh, apply your recurrence. So let's try to use that thing on this graph and find out what is its chromatic number. So in this graph, what is the largest independent set? So we have,
Yes, yes. So the vertex number, like say, if I say vertex number 2, um, and vertex number 6, and 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 vertex number, say, 7 cannot be considered. No, 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 no. So, and I mean, I just have, yes, an independent set of the size 2.
so how about 1, 2, and 3?
Okay. So, uh, yes, yes, 1, 2, and 3, yes, yes, it is better. Yeah,
How about 4, 5, and 6?
yes,
So if you do not look at 7 at all, let us say 7 does not exist, then this is a bipartite graph where the two partitions are 1, 2, 3, and 4, 5, 6.
right, 2 color. 2 plus 1, 3. Its value would also be equal to 3.
Yes. But uh, yeah, so let's try to apply your thing. So you said that, okay, I have a graph. The first step is I would like to compute what is the largest independent set. So 1, 2, 3 is an independent set, 4, 5, 6 is also an independent set. Arbitrarily, let us say we pick 1, 2, 3 as an independent set. So we know that only one color is sufficient to color 1, 2, 3. So 1, 2, 3 can get the same color. All right.
Yes, yes,
Now when 1, 2, 3 is removed, then the graph that is left is like this. Uh, okay, so there's an edge between 4 and 7, so it will require two more colors. So yeah, fine. So 1 plus 4 and 7 will require two more colors, and 5 and 6 can get one of the colors that is used for 4 and 7. So 5 and 6 can get the same color, but 4 and 7 would require distinct colors. So finding the largest independent set in this case at least did not give any explicit benefits, because 7 itself is an independent set, and once you remove 7 you have a bipartite graph. So 2 plus 1 colors is also sufficient. I mean, it is easy to see that removal of 7 leads to a bipartite graph, which means that 2 plus 1 colors are required for this uh, graph.
But then my point here is that, say, once you remove the vertices 1, 2, and 3, then for the remaining graph, again you focus on the largest independent set only, comprising of, say, 4, 5, and then 6. So if you proceed in this way, then probably in this case, apparently we are not getting any benefit. But for the complex graphs, if we use this greedy approach, then probably we may find, or at the most, it may so happen that the algorithm terminates early compared to the this previous approach.
This can happen, but yeah, in most cases this is likely to happen, but theoretically speaking, we may not gain anything in terms of running time, uh, but
Yes,
in practice it might help.
yes. Because we are working with the problems which are really computationally intractable, so there won't be much improvement in the execution time. Practically, we can see an early stop of the execution of the.
Yes. So yeah, I agree with you. So again, we'll look at an independent set question. So here's the next question on independent set again. Just a second. Okay, so figure 1 also needs to be seen simultaneously. So let's look at figure 1 again. What happened? Wait, this is not figure 1. This is figure 1, yes. Right. So let GS denote the number of non-empty independent sets in G of S. So G of S is the subgraph induced on S. Okay, so S is some vertex set and G of S is the subgraph induced on S. Okay. So how many non-empty independent sets are there in GS? That is the question. So this is my graph.
Yes. So, like in the case wherein we do not consider any vertex, say phi. So, what's the meaning of phi here? That no vertex is given to us, and still
Yes,
there are
yes, yes.
that, yes, non-empty independent set. So in this case, there does not exist any non-empty independent set. So therefore, this value is zero for sure.
That is correct.
Yeah, and so if we have two vertices u and v, And so U and V, and now they're asking that how many non-empty independent sets exist. So U and V both are connected. So you and me both are connected. So I mean, this is going to be so U and B. I mean, if I consider so there does not exist any independent path. So I mean, for UV, there will exist an empty independent set, and which is being denied in the question. So option C cannot be correct. And for the WB, yes, so WB we can have an independent set and having two elements.
Mm-hmm.
So they are asking, they are saying that the graph induced by including W and V. So there is no connectivity. But then if I consider UV, then also, okay, yes. So if I consider WB, so the independent set would comprised of say how many independent sets would be there? So how count of the independent set uh, for I mean W and V. So there would be two independent sets. One is V, other one is W. So this is also not correct. And G comma 3. So the meaning of G comma 3 here would be what? That do we have an independent set of the size say 3? Do we have three independent sets for this G? So if this is the interpretation of G comma 3, then how many independent sets are there? So G comma 3. So do we have, or I mean, what's the meaning of G comma 3? Is it the largest size of the independent set? Is 3 or what?
So I think that G comma 3 in this question is asking that does there exist uh, does there exist sorry this does there exist is written like this, does there exist, oh no, so I think this is with respect to chromatic number. So is three colors sufficient for coloring the vertices of G?
Oh, I see. So just now we have seen this G comma 3 alias instance.
Yes.
So, so yeah, so I think only the first and the last options are true and rest all are false.
So let us look at this question. So how many independent sets are non-empty independent sets are there for the subgraph induced on U and V? So U and V is an edge, a
Yeah,
single edge. So U alone is an independent set, and V alone is also an independent set. So,
yes.
but U and V together is an edge, is not, so they do not form an independent set, is not an independent set.
Oh, I see. Yes. So then the next option is also correct. GW comma B would be equals to 3 then.
Yes, yes. So, uh, these two vertices W and V, they induce a graph where W and V are singletons, or other what is call it, pendant vertices with degree 0. So W alone is an independent set, V alone is an independent set, and W V together, there is no edge between W and V, is also an independent set. So you are right. So there are three distinct non-empty independent sets. So at this point, we can take a break, or maybe the next question is simple only. The next question is on set theory. This is something that we have seen in school. Maybe we can look at it in 10 minutes. So this is union of, so how do you write an union of multiple sets? So we have seen in school that if you have union of A and B, two sets, there's a Venn diagram of A and B. So there's some universe. from which set A and set B are taken. So A union B can be written as, so they are taking cardinality, but right now I'm just taking, so this is A, I mean, let's take cardinality only, plus B. So this entire thing plus this minus A intersection B. This is from the inclusion and exclusion principle, that if you take all the, if you count all the elements in A once, count all the elements in B once, then you have counted A intersection B twice. So you should deduct once A intersection B. So now this inclusion exclusion principle, how do you generalize it for n sets?
Yes, so I mean, for the singletons, we would be considering individually, we would be adding, including, and then we would be subtracting all the sets, I mean, as a tuple, and then again including as a triple. So this is the principle of the inclusion and the exclusion. So I mean, you can write it like say, so initially the summation of the AIs, like say, if I consider A1 union A2 and say till union AN, so then initially I would be writing the summation, so sum of, I mean all the AIs, and
Yes,
then I would be including and then excluding what? Excluding minus the summation of AI intersection AJ, and then yeah. So if I've been given n number of such things, then its mod is equal to the summation of mod of AI, and I very strong, the summation over I, and, yeah. Uh, and then excluding 1 to n, yes, and then excluding the mod of AI intersection AJ, and J should be greater than I, say for the simplicity, and then we carry out the summation from 1 to n kind of a thing. So I, J is greater than I. I mean for I comma all I comma and for all J, yeah, yeah, yes. And then again including this thing, say if I want to, if you want to write an additional term, then summation of the mod of AI intersection AJ intersection AK, and wherein K is greater than J is greater than I, and then similarly for all the I's. Uh, and yeah, and the last term would be, it depends on whether the value of n is even or odd. So therefore, better we write the last term as plus or minus whatever, say plus last term, and minus 1 raised to the power, say n plus 1, and then the mod of A1 intersection A2 and then till intersection AN. So this minus 1 raised to the power n plus 1 will manage everything, I think, because if n is even, so then
mhm.
minus 1 will become, yeah, then even thing, so then everything is going to be, I mean, it will manage it.
Yes, 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 yes. So when you are taking intersection of one set, three sets, five sets, odd number of sets, then there is positive contribution, and
Yes,
there is negative contribution when you are taking intersection of two sets or maybe four sets and so on, even number of sets.
okay,
So minus 1 to the power the size of the set plus 1. So size of the set is 1 here. So this is positive contribution. Now, when the size of the set is 3, there are 3. I mean, size means how many sets are being taken intersection of. So here in this second option, it says that okay, so you are taking some subset S. So n is what? N means, capital N means the set of the indices of the sets from 1 through n. So if you are taking some subset of n, which, that means how many sets you are merging. If you're taking odd number of sets, so if mod s is odd, then mod s plus 1 is even. So minus 1 to the power even would turn out to be positive. So that is why this is correct. Whereas this one is incorrect because if you're taking, if you're merging, if you're taking intersection of odd number of sets, they should give a negative contribution, but we have seen that odd number of sets should give positive contribution. There's one more subtlety that the number of sets you are merging should be non-empty. So for example, here also you have seen that all the terms are either one set or two set or three set. There is no empty set being merged. So that is why this is correct. Is that fine?
Yes, yes, yes.
On the other hand, the next two options are asking that how many sets, sorry, how many elements of the universe are outside of the union. So look at this Venn diagram. So we want to count how many elements are in this region outside of A union B. So whatever we had counted have to be negated. So first of all, we have to count how many elements are there in total in the universe minus A union B. So whatever terms we had here, they will change signs. So this would become negative, this would become negative, this would become positive. And of course, we have to have the universe size here. So mod u minus this plus this and so on. So first observation is that the terms here are changing signs. So one more change here is that this summation is taken over all subsets of the index set, including empty set. So if S is empty, what is happening? So if S is empty, that means this entire thing is empty. So if you're not, so you're taking intersection of nothing. Okay. So summation over, just a second. So we have to find this part. So u minus this part is what? That is, we want to find an expression for this. So u minus A union B should look like mod u minus mod A minus mod B plus A union A intersection B. Okay. So now all these terms have to be there, plus additionally this mod u has to come from somewhere. How many elements are outside of A union B? How will I know?
So I mean to say, so actually, um, so the thing is that um, um, so here they are asking, actually the principle of inclusion and exclusion is used in this sense only. In the sense that it is being used in the negative sense. So like
Hmm.
the U is having all the possibilities wherein no property is being followed. And say A1 is having wherein some properties are being followed, or A2 indicates again some properties are being followed. So that is what I mean. We got this formula that all the properties are being followed minus the properties which are being followed as a tuple plus including all the properties which are being followed as a triple kind of the thing. So now the point is that if I compute this A1 intersection, A2 intersection, and intersection AN. So, and if I take its complement, so
Mm-hmm.
that will as u minus something. The question which they are asking. So actually the expression which they are asking is nothing but a1 intersection a2 intersection a3 and till intersection an and its complement entire. That would be equals to u minus this stuff. I mean u minus this inclusion and exclusion.
Mm-hmm.
So yeah, so we should get something and which is a1 intersection a2 intersection a3, but then a complement should also be there. So yeah, that is what I mean to say, because U is the universe of the discourse, and you can use De Morgan here straight away. So if you can you write this expression here, which I said just now, say A1 intersection uh, A1 intersection A2 intersection A3 and so on, say till intersection AN and its complement of that thing. So what this value is? So if we use De Morgan, so that will become what? That is U minus the A1 union A2 union A3 this entire. That is what they are asking right.
Hmm.
So actually their question is, I mean this only. But I do not find this. I mean there is a difference of S and S plus 1 only in the second last and the last option. So out of these two, which one will correspond to the intersection thing and its complement?
That is true. So in the expression of the union of the n sets, -1 to the mod s plus 1 was used. So now these terms which were in the union, they will change signs. So from that sense, these two should not means if you have to change signs, then you have to either deduct one or add one to the exponent. So mod s makes sense. This does not make sense because you are taking the complement which you said.
Yes,
So,
yeah.
but on the other hand, how does so from the figure I want to understand that how does so you want to compute u minus these things. So you want to basically compute how many elements are not in A union B. So other than
Yes, so like in this case also, if you are computing that U minus A union B. So if we
hmm,
simplify this is nothing but A intersection B and its complement.
A intersection B is complement.
A complement, I mean A intersection B, yes, yes, A intersection B and its complement. Because if you solve A intersection B and its complement, that would be A complement union B complement. And if I take A complement union B complement, then I will get the shaded area, this U minus this entire.
Oh, okay, okay. So you are saying that okay, let's do it for this part only. You are saying that A union B complement is A complement. Let's
No, no,
use
no, no. I said A intersection B complement.
okay.
A intersection B complement. Yes, and this complement is equal to what? The complement of A union the complement of, and that is nothing but the
Oh,
shaded
that's
area.
that is true. That is true. That is the De Moivre theorem.
Yes, yes, yes.
So they are willing to compute the complement of the union of so many AIs.
Uh, yes, because I think in the principle of inclusion and exclusion, it is easy to compute this thing. A intersection B, rather than computing A union B, uh, because I mean, because of the obvious reasons, yeah, because of the obvious reasons. Uh, so yeah, but the thing is that I mean, they are representing this complement thing just by this mod of s or mod of s plus 1. So basically, their question is that if original thing is minus 1 raised to the power s plus 1, then what its complement is.
Hmm.
That is the point. And except this thing that all the signs will get reversed. So therefore, instead of using, say, if we are using minus 1 raised to the power mod of s plus 1, then the other side we should use minus 1 raised to the power s. But it does not contain that fact that what this mod of u here is and how that u thing has been removed from
Yes,
here.
yes. So how they're, that is true. That is my concern, that how they're, so they're taking, if they're taking the negation of A union B. So they, for example, if there are, let's say, 50 elements within A union B, so this term is going to give minus 50. But let us say outside there are 30 elements. So overall there are 80 elements in the universe. So 80 minus 50 should come. So where is plus 80 coming from? That is not clear to me. So I'm saying that
Yeah.
if A and union B together is, let us say, 50, but outside there is 30. So U minus A union B should be 30. So this should look like 80 minus 50. So where is 80 coming from? That is not clear to me. So let us do one thing. We'll take a break now, and then we come back. We will spend 1 or 2 minutes on this to understand how this expression is correct.
Yes,
And then
yes.
we'll also discuss two more questions, then we will finish today.
Sure.
So shall we meet at 7:20 now? Now it is 7:08, so 7:20 we can meet.
Sure. Yes, yes.
Can you hear me?
Yes, yes, I can hear.
So I just looked up the lecture. So in the lecture, they have made a convention. So the difference between these two entries is that here the summation is over all subsets of indices except phi. That means all subsets of n are allowed except phi. Here phi is also allowed. So s could also be phi. And when s is equal to phi, so s equal to phi, then what happens is this term. So this term is saying that intersection of I belongs to S. So that means I belongs to phi. So that means it's empty. So this intersection of nothing is by convention is equal to the universe. So this is by convention. So that is the convention they have made, that if you are taking as empty subset, then the intersection over all AIs where indices I are empty, that is the entire universe from where the elements are being taken. So that is by convention only. So there's not much we can do. That is why. So this one term in this summation, which is corresponding to S equals to phi, is the universe. And now the universe minus A union B is nothing but A union B complement. So minus A union B, how do you achieve? Just by reversing the signs of the expression in of A union B. Now, how do you change the signs of the terms in A union B? You so whatever was minus, you make it plus by changing the exponent from mod s plus 1 to mod s. So that is how this is the correct one, and this is not the correct one because here the terms, individual terms in the summation have the same sign. So this is not the correct one.
Yes, and I also made a mistake. I felt later that so A union B and its complement is equal to A complement intersection B complement. So uh, yes, yes. So yeah, A complement intersection B complement. So yes. So yeah. So therefore, A1 union A2 union set in An and its complement is equal to A1 complement intersection A2 complement intersection A3 complement and so on in set in intersection An complement.
Correct,
Uh,
correct.
yeah,
Hmm.
so that is how this negative this principle of inclusion and exclusion is used in the negative sense.
Yes. So this is A complement, and if you take B complement as well,
Yes.
then you will get that is so. This statement is not correct.
This statement is also correct. It is also fine. But the way in which this principle of inclusion and exclusion is being used is like this.
Okay.
So, yeah,
So A complement union B complement is A intersection B's complement. That seems correct. So what you said is also correct, but now whatever you're saying is also correct.
yes,
Uh, yes, yes. But you are
because
saying that this is more appropriate in this setting. That's what you're saying.
yeah, in the setting of the inclusion and exclusion, because it
Mhm.
is easy to show that I mean the meaning of the complement of A would be that a particular property is not being followed. So rather than showing that n number of the properties are being followed,
Mhm.
sometimes it becomes easier to show that the one particular property is not being followed and the other property is also not being followed, and then so on. In that sense.
Hmm.
Like we used to compute the integral solutions of, say, x1, find the number of the integral solutions of x1 plus x2 plus x3 plus x4 is equal to 32, say, under the constraint that x1 should be in this interval or x2 should be in this interval.
Mhm. Makes sense. Makes sense. Okay. Fine. So we have recapitulated inclusion exclusion principle after a long time. So good only. So two more questions are going to be there today. Uh, right. So Yeah, this question is interesting. This is so today's topic is the use of algebra, so algebraic. So this is an algebraic question. Ah, is a font large enough?
Yes, yes, I can read it. That which of the following elements are true? Assume that P is not equals to NP. So we are assuming here that P is not equals to NP, and then counting the number of the triangles in a given n vertex graph is NP hard. Uh, so counting the number of the triangles in a graph in a given n vertex graph. Uh, so we have been given n vertex graph. So what this? Okay, okay. So does there exist a cycle of the length 3? Okay. So how many cycles are there of the length 3?
So for example, suppose this is a graph. So how many three cycles are there in this graph? So one of the cycles is 1 to 4, and another cycle is 1, 3, 4. Is there any other cycle of
Any other
length 3?
length 3? No. No.
So is it possible to find the exact number of three cycles in an n vertex graph in polynomial time? That is the question here.
Okay. Okay. So uh, yeah. So I think that we can take the help of the adjacency uh,
Yes.
list or adjacency matrix representation.
Let us say the adjacency matrix of the graph be A. So what is the adjacency matrix? The adjacency matrix is a matrix 0 1 matrix, particular value. So if ijth entry is 1, so aij is 1 if and only if there is a direct edge. There is an edge between vertex I and vertex j. So now with some manipulation of the matrix, turns out that we can count uh, how many triangles or three cycles are there in the graph.
So I have something to say here that if we compute say from the A, if we compute A square, the adjacency matrix say for A square,
Mhm.
then between any two element there would be one element. And if I compute A3, a raised to the power 3, then in
Mm.
between any two elements there would be two elements. And now, I mean, in the A3, if I find that the entry corresponding to 1 and 1 uh, came out to be, say, so basically this is related to not to the, yeah, something similar to the adjacency matrix, but more related to the transitive closure of, I mean, kind of the thing. Because we can represent a relation through a directed graph also.
Mhm.
So I need to say that if we construct a raised to the power 3, then okay, so there it will show that there are two elements, and then if corresponding to I and I, if I find the entry as 1, I hope that we would be able to construct, yeah, solve this thing in the polynomial.
Yes, so some matrix multiplications are required. So specifically, if you compute a cube, then by looking at the matrix a cube, you can tell certain things. But before answering that question, maybe the last two statements we should evaluate. So what is the meaning of the uh, multiplication of the matrix a k times? So what does a to the k represent?
So yes, so a raised to the power k would represent that say so yes, so a raised to the power k. My interpretation is that say uh, like the A matrix shows that whether two elements are directly related or not. So
Yes.
meaning of A square would be that, say, like one vertex number one is related to the vertex number two in the matrix A square, because in between I can reach to the vertex two from the, I mean, vertex one with another vertex in between, the vertex four here.
That is correct.
Yes. So yeah.
So let me take an example and we will understand. So once we see the example, then we will remember it. So let us say I take a simple graph. So let us say my graph is a triangle. So let us say this is vertex 1, this is vertex 2, vertex 3. So now I can write the adjacency matrix of this graph. So this is 1, 2, 3, this is 1, 2, 3. So one is not connected to itself, but one is connected to 2 and one is connected to 3. Similarly, 2 is connected to 1 and 3. 3 is connected to 2 and 3. So this is the adjacency matrix A corresponding to this graph. Okay. So now I'm going to compute A square. Maybe I'll just compute it here. Multiplying A with A.
And this would be a Boolean product.
No, this is matrix multiplication. It need not have 0, 1 entries only. So I'm first computing this first entry of the matrix. So this row is multiplied with this column. So 0 to 0, nothing. 1 to 1, 1, 1 to 0, 1. So this entry is, have I made a mistake? No, so 0 to 0, 1 to 1, 1 to 0. So this, just a second.
So this value would be a one.
Okay, this is 1. Then first row, second column, 0, 0, 1. Okay, then first row, third column. This is 2, isn't it?
Yes. So what could be the interpretation of two here then?
Now first, let us do the multiplication.
Okay, okay. So first row and the, so first column entries are open. Then for the second one, second row and the first column. So this entry will come out to be zero, and the next entry would be two, 0, 2. I mean, first is 0, yes. Next entry is 2, and the next entry would again be equals to 2. So 0, 2. And then we have third row. So then the entry will become 1, and then 1 again. So it is 2. I mean, this entry would be 2. And in the third row, the first value would be a 1, and the second value would be a 1 again.
Oh, I have
And
made a mistake here. Sorry. So this is a mistake.
3, 2, 1 would be,
Uh, 3 is connected to 1.
yes, so this value would be 1.
So, but 3 is not connected to itself. So that is the problem. So that's why slightly, because I did the calculation earlier, there was some mistake happening.
Yes,
Sorry about it. Let's do the calculation once again.
yeah. So this 3, 2, 1 entry is the 1, right? So yes, so 1, 1, 0, and here also it is 1, 1, 0. Then the entry in the first row and the first column would be equals to a 2.
Correct.
Yes. And first row and second column, so this entry would be a 1. And then first row and third entry, this would be a 1 again. And then second row and the first column, so this entry would be a 1. And second row and second column, this would be a 2. Second row, third column, and this entry would be a 1. And then third row in the first column, so this entry would be a 1. And again, this entry would be a 1. Next entry would also be a 1. And the last entry would be equals to a 2.
Now we can analyze that what does a square mean. Okay. So we have computed a square. So now look at the entry corresponding to 1 1. So it means that so from 1 to 1, so there are, in how many ways I can reach 1 from 1 itself in 2 hops. So a square means you are allowed to, so the length of the path, or I will say, so walk. So there's a difference between walk and path. So walk means, so for example, if you are going from 1 to 2 and then coming back to 1, I can call it a 2 length walk.
Yes, one element in would be.
Come again.
One element in one wheel. If the length of the path is 2, then there is one element in one wheel. And if the length of the path is 3, then there would be two elements in one.
Correct. So the point is, 1 is repeated. So it's not a path, it's a cycle essentially where I allow repetition, then we call it a walk instead of a path. So it's a 2 length walk because there are 2 edges involved. So I go from 1 to 2 and then I return to 1 again. So in how many ways I can reach 1 from itself using a 2 length walk? So in 2 hops, I want to start from 1 and come back to 1 using 2 hops. So one is I can do this. I can go to 2 and come back to 1. The other is what I can do is I can go to 3 and come back to 1. So there are 2 distinct walks of length 2 of reaching 1 from itself. This is the 1 to 1 1. So this is the interpretation. Now this is the entry corresponding to 1 and 2. So the how many 2 length walks are there from 1 to 2? So it's saying that there is exactly one way you can go from 1 to 2 using 2 hops. Is that fine?
Yes, yes.
So
You
this
can mark
is,
last entry of this matrix as 2.
oh yes, yes, last entry I have not written. Yes. So the I comma jth, so the I comma j, this is what it is saying that let ak denote the kth power of the adjacency matrix. The entry in the ith row and the jth column of the matrix A to the k gives the number of k length walks from vertex I to vertex j. So from the small example, this triangle, we can see that for a square, that is the truth. So there is a difference between path and walk. So path is incorrect. Path means you do not allow repetition of vertices, but walk is you allow repetition of vertices. So this is true and this is false. Now we can go back to the first two statements, that how we shall count the number of triangles in an n vertex. So as you suggested, we'll compute a to the 3. So now we have a to the 3. Now in this example, we can do this. So if we multiply this matrix with a once again, then we'll get a to the 3. Let's do this multiplication. I will do it quickly.
So if we so while computing A3, I think that we would be taking product of A with A square and not A square with A. So if we follow this thing, So then the first entry will become the first row and the first column. So the entry will become 2. And so the first entry of A3 would be 2. And first row and the second column. So this entry becomes 2 plus 1, 3. Uh, and first row and the third column. So this entry becomes 3 again. And second row and the first column. So this entry becomes 3. First entry of the second row is 3. And the second entry of the second row will become second row and the second column. So this value becomes 2. And second row and third column. So this entry becomes 3. And then third row and the first column. So this entry becomes 3. And third row and the second column. So this entry becomes 3 again. And third row and the third column. So this entry becomes 2.
Correct. So now looking at this A cube matrix, can we answer that how many triangles are there uh, in this graph?
So yeah, like say, so can you write the vertices number here along row side and along column side? Uh,
Okay.
yes. So the length in between 1 and 2. So I can reach in two different ways to the vertex number 1 to itself and with a path length of 3. So what does it mean? Yes. So this is one way, and 132 could be the my other way. All right. So yeah, and so say from 1 to 2, I can reach in, but then I would be focusing on
We should
uh,
focus on 1 to 1 itself or 3 to 2 to 2 itself.
2 and
And
then 3. So
yes.
there's just three cycles, three triangle cycles here.
Yeah, so it is possible to get a triangle from 1 to itself in two ways, but this is the same triangle. Similarly, from 2 to 3 also is the same triangle. So somehow, so although it looks like there are six triangles, but the six triangles are identical, that also has to be identified in some way. But the point is, in polynomial time, one can find the total number of triangles in the graph. How to detect duplicates? I think that part is discussed in the video, but it's doable algebraically. So as far as this question is concerned, we can do it in polynomial time. So this exercise was sort of to gain confidence that we can do it.
And what this exercise has to do with this thing that we assume that P is not equals to NP, we did not use this thing anywhere in the argument.
As I don't know about it, so why is it necessary? It's not been used. You are right.
Yes, yes.
So that is probably not necessary, but I do not know the reason.
Yes. Yeah. Because I thought that probably, I mean, at some point of the time, we would be
Mhm.
using non-statistic algorithm. But then other things came out to be, I mean, polynomial. So therefore, I mean, this is just a line and does not mean anything else.
Yes, yes, yes. That is my feeling as well. So you remember that some weeks ago we were discussing this max 2 sat problem. So you said that okay, 2 sat itself is polynomial time solvable. Then what is the meaning of max 2 sat? And
Hmm.
then
Yeah. Yes. Yes. So we, I mean, you gave clarification in the next class that actually solving two satisfiability problem is easy, but then this max thing actually would be difficult. That
yes, in case the given formula is not satisfiable, then what is the maximum number of satisfiable clauses? Finding that is not easy.
yes.
So same thing is there in the next exercise today. So max 2 set and max 2 CNF set are the same thing. CNF you can ignore for now. CNF is conjunctive normal form. So we are basically looking at the max 2 set question, that you are given a 2 set formula and maybe it is not satisfiable. So you can decide in polynomial time whether it is satisfiable or not. But once you conclude that it is not satisfiable, then what is the maximum number of satisfiable clauses you can have? So for this problem, uh, okay, so they describe one algorithm. Uh, so I'll tell you the algorithm briefly. So first of all, the naively, if there are three, so if there are 3n variables, then there exists 2 to the 3n possible assignments, truth assignments. Because for every variable you have two options to set it true or false. Okay. So that is the naive running time you will have. So for every assignment, you can check how many uh, clauses are getting satisfied, and then you can report that for which assignment maximum number of clauses are satisfied. Okay, but to get a running time which is slightly less than 3 to the power n, there is some trick that has been described in this uh, lecture. So what they have done is, so let us say that the variables are numbered like v2, v1, v1, v2 up to 3n. So these are the variables, this Boolean variables. So they have partitioned the Boolean variables into three parts. So each part has n variables. So the first n variables are here, and then vn plus onwards till v2 n variables are here. 2n plus onwards remaining variables are here. So n variables each in each partition. Okay. So now, so how many possible truth assignments are there for the first n variables? How many possible truth assignments exist for the first n variables only? For this part.
I could not understand this question. How many possible truth assignments exist for which part?
So this is part 1, this is part
Yes.
2, this is part 3. Okay.
Yes.
So according to the question, the total number of variables in the formula, the Boolean formula is 3n. So let us say these are the variables.
Yes.
And I partition these n variables into three parts. Let us say this is v1, the first n variables, this is v2, the next n variables, and this is v3, the next n variables. Now I am asking that for the first n variables only, how many possible truth assignments are there?
2 raised to the power n.
Correct. So there are 2 raised to the power n possible truth assignments for this part. Similarly, 2 to the n possible truth assignments for this part, and 2 to the n possible truth assignments for this part. Okay. Now, for each of these assignments, so now the goal is to construct a graph. So the goal is to construct a graph where the vertices are corresponding to the different truth assignments. So now the total number of different truth assignments is only 3 into 2 to the power n. So observe that earlier your total number of truth assignments were 2 to the 3n. Now it has been reduced to only 3 to the 3 times 2 to the n. So that is the total number of assignments you have, and corresponding to each such assignment you will construct one vertex in the graph. So that is the first part of the question, that this graph has how many vertices. So that is the first part of the question. So this is the total number of vertices. So is that all right?
Yes, but then dividing this entire set of the vertices into these three partitions would require, certainly would require some efforts. Uh, uh, because I mean, otherwise, how would I come to know that okay, these vertices are there in the first partition and these vertices are there in the second partition?
So the way they do it in the algorithm is they make an arbitrary partition. So they take any n vertices as the first part. Now out of the remaining 2n vertices, again they make a selection of n vertices arbitrarily and call it the second part. And then the remaining vertices form the last third part.
Okay, so if I pick one truth assignment from the first partition, is it necessary that such a truth partition will make the entire I mean Boolean expression having three n number of the variables satisfied?
That is not necessary. In fact, we assume that the Boolean formula is not satisfiable. So the Boolean formula cannot be satisfied by any truth assignment. Now, how many clauses you can satisfy at the most? That is the question we are interested in.
Yes, so then, but then this is not a true reduction, say from 2 raised to the power 3n to the 3 dot 2 raised to the power n. Because by exploring 2 raised to the power 3n number of the possibilities, we will definitely come up with a truth assignment if it exists. And however, after exploring this 3 into 2 raised to the power n number of the possibilities, I mean, virtually we are not getting, I mean, in reality, we are not getting anything out of it.
Mm. So I understand your objection. So you are saying that, so I think what you are saying is the following. So you are saying that, okay, so earlier there were so many possible truth assignments. So this was equal to 2 to the 2n into 2 to the n. Now, instead of 2 to the 2n, I have put 3. Then so many, there's such a huge reduction in the number of possible truth assignments. Then this does not look like a correct equivalent thing.
Yes, because the interdynamics among the variables has been lost somewhere. I mean, in this process of partitioning this thing.
Yes, yes, yes. That is true. Very much true. There's a huge reduction. So whereas 2 to the 2n is an exponential thing, whereas 3 is a constant. So of course, these two are, so whatever is being captured by the original truth assignment is not being captured by the reduced truth assignment. That is true. I agree with you.
Yes. So what is your question? That how many vertices would be there? So certainly there would be 3 into 2 raised to the power n number of the vertices.
Yes, yes. So for every partition, they are looking at how many truth assignments are there. So in this case, there are 2 to the n truth assignments here, 2 to the n truth assignments here, and 2 to the n truth assignments here. So they make so many vertices. Now so among the vertices, they are putting the edges so that it becomes a complete bipartite graph between every partition. So now, so you can think of these truth assignments as parts. Now between parts, you are putting edges so that it becomes a complete bipartite graph. So it's a complete multi-parted graph now. So now the question is how many edges they have to put. So think of every part having 2 to the n vertices. And now the question is to make it a complete multi-parted graph, how many edges should be there?
So complete in the sense that for every vertex in the V1, I would be connecting to every other vertex in the V2. Is this so?
Yes, 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 yes.
Yeah.
So for
So
every
that
vertex, you have to draw 2 to the n edges.
yes, so 2 to the n into 2 to the n, and this value will come out to be what? Uh, a raised to the power x or a raised to the power y. So this will be 2 raised to the power 2n number of
Yes.
vertices at this point. And 2 raised to the power 2n more. So therefore 2 raised to the power 2n plus 1, uh, or 2 into 2 raised to the power n. And then,
Yes.
yeah, and so 1, 2, probably 6 into 2 raised to the power 2n, I think.
So between V1 and V2, you have one complete bipartite graph. Between
Yes.
V2 and V3, you have one complete bipartite graph. And between V1 and V3 also, you have one complete bipartite graph. So the three things are there. So these three things have to be summed up. Each term is 2 to the n into 2 to the n, which is 2 to the 2n. So 3
Yeah.
into 2 to the 2n is the total number of edges. And that is the option 3. So that
Yes.
is to, yeah, so that is the overall. So now that is the first step of the algorithm, that how do you construct that graph. Now on that graph, you do certain things to be able to answer that question. So then finally, the running time becomes something smaller than 2 to the 3n, but that is outside of the scope of this question. So of course, as you have observed, that as soon as you have drawn this graph, there is some exponential loss in terms of the uh, representation of the problem. But in spite of that, they are able to do certain things. Some tricks are there that the running time is reduced, but you are able to answer how many clauses are satisfied at the most.
Yes. Yes. So
So yes,
yeah, so I have a small request to you regarding the last session, which is on 21st. That can you take two problems? I mean, one problem wherein you show that FPT is possible, and so that along with the typical steps of which are being used in FPT. And
yes,
second problem wherein kernelization is being done, and uh, so again the typical steps of the kernelization, and that would be really helpful to, I mean, summarize this entire course, I think, because we studied these two major techniques in this course.
okay.
And
So
yeah,
you want to see uh, two examples, one where the fixed parameter tractable algorithm does not use kernelization and the other one uses kernelization.
yes, yes, yes,
Okay. So one problem I have already sort of selected, it's tentatively selected, where it's a problem of geometric flavor. So so the question will be very simple to explain. You can explain it to a high school going question. So it's going to be an NP-hard problem, and then certain geometric tricks are necessary to arrive at the fixed parameter tractable algorithm. So that is something I will discuss, and I think this will be the first problem of the session, and this is going to be interesting. And second problem, as you said, some problem that requires kernelization, that I will select soon.
yes, yes.
So
So
you had,
even
yeah, go ahead.
yeah, so even if you select the second problem, the one which has already been discussed, it's okay. I mean, already discussed in the previous lectures, it's okay. But then at least the process of using, I mean, this showing this correlation would become clear.
Okay, okay. So I will take some toy examples so that it is easy to explain, and also it should explicitly express all these steps. So I will try to make it as clear as possible. But you had also suggested one question that you are interested in, which is not of FPT nature. So would you prefer to skip that question in favor of these two things?
Yes, yes, yes. Because I mean, these two problems will summarize the entire course thing. So yeah, it would be, I mean, helpful for the others as well, and who would be viewing you, I mean, these sessions later. So it would be helpful for them.
Yes, 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 yes. So, all right, all right. Okay, so I think, yeah, you're right. So these two things should sort of conclude this course conceptually, and this would be a natural conclusion for the course.
Yes. And so yeah, and I was looking for another material, or another something, I mean, easy to, and this small book kind of the thing on this parameterized complexity. So I found this book, and I wrote the name of the book in the chat. and wherein there are two chapters dedicated to the parameterized things, and I found few simple examples in this book. So this is these are the chapter numbers five and six.
Okay. So this
Yeah.
book, who are the authors?
Yes, so I tell you the name of the authors of this book. So these are this is written by yeah.
Okay. The multiple authors.
Yeah, chapters 5 and 6.
Chapters 5 and 6, they discuss reductions. Do
Uh,
they?
Parameterized complexity and reductions.
Oh, middle, middle. Fine. So we are going to discuss reductions and complexity in the 12th week.
Yes.
So if there is anything that you would like to ask, we will discuss in detail on the 12th week.
I have not gone through this book completely, but then because some of the examples are really difficult for me to understand, I could only understand simple examples.
Mhm.
But yes, if you can find some good examples from here, that would also be good. Because then I would be having some material with me, and later on also I can refer.
Yes, yes. So if there is anything, so you said chapter 5 and 6.
Yes, so in this book, these two uh, chapters are.
Okay, okay. So if there is anything specific, any particular lemma or any particular claim that you have doubts on, then I can also take a look at it and we can discuss next time.
So as such, I am not. I could not find time to. I could
Yes, yes.
only go through these chapters quickly, and then I thought that okay, things are a bit difficult for me now, but later I can actually go through these two chapters in detail. So if you can pick up some problems from here also, that is also fine. Otherwise, I mean, these two things are
Oh, okay,
also.
okay. All right. All right. So you were suggesting that we can have some discussion from this book. Fine. All right. Okay. Thanks for the suggestion and thanks for coming today. I'll see you on Monday next week.
Thank you
And
so much.
Prabnur also. Thanks for coming, Prabnur.
Thank you so very much. Good night.
All right. Good night.